All right, hi everyone. It's great to be back at Discuss for another year, and our session today is on new frontiers in space exploration. I'd argue that we are sort of in the middle of three overlapping revolutions in space exploration. The first of which arguably maybe we're at the tail end of and kind of made the beginning of my career, was miniaturization, right, and the emergence of CubeSats and all that came from that. The second one that I'd say we're squarely in the middle of still is the dramatic reduction in launch costs and the emergence of SpaceX and other companies that are expanding access to launch. And maybe the third one that we're just at the beginning of, that we heard a lot about yesterday, is the emergence of AI and machine learning and its application to space exploration, both enabling more autonomy for missions and more data analysis that we can do on the ground. And we're about to hear from 6 speakers on a whole range of topics, both from academia and government. A quick announcement that one of our speakers, unfortunately, Hugh Mortimer, is ill and will not be joining us today. But I guess we'll kick things off with Carly Howett, who's a local, associate professor of space instrumentation here at Oxford, who studies the surfaces of icy worlds in the outer solar system and has worked on a whole bunch of really cool missions, including Cassini and New Horizons, and is going to tell us why we should all be really excited about missions to the outer solar system. Thanks.
Exactly. Okay. All right, good morning, everyone. Thank you for Breakthrough for having me here. As Zach said, I am a local. I'm based now at the University of Oxford, but I was at SWRI for 15 years, so it's nice to see some SWRI folk here as well. And I wanted to talk a little, when we were planning this session and I was asked to give a talk, I was trying to think about what would be a useful contribution to this talk. And we have so many excellent talks in this session, all about the technology that is that's driving our ability to explore. But I wanted to take a step back. I'm a scientist, not an engineer, and I wanted to talk about why we're bothering exploring in the first place, right? The outer solar system, haven't we seen it all? We've sent missions there, we've seen it, why bother going back? And so this is supposed to be a bit of an overarching talk. I did go back and read things like the Decadal to try and get a sense of where the community is at, which is always fun. But of course, this is my answer to this question. And you ask 100 scientists what the most important questions are of the day, and you'll get probably 200 answers as they try and figure it out. So with all that said, I thought before we kind of lead into where we should be going and what missions we need, taking stock of where we're at is a good first point. So this is a NASA chart, and it is very US-centric, but it does include partners that NASA have. So anything that NASA is collaborating with the European Space Agency or the Japanese Space Agency will be included. And it's a bit of an eye chart. I'm not expecting everyone to read all the little details, but it kind of gives you a sense of where we're at. So on the left-hand side, we have the Earth, and everything shown in green are Earth missions. The band across it is the International Space Station, so all of those shown in orange are instrumentations that are on the International Space Station. This is the moon with lots of purple instruments and missions going there. We have our astrophysics on the top left. And then scattered through the main bit is the inner solar system. So we have Mercury, Venus, Mars. And you'll see lots around Mars. And that's all I'm going to say about that. And then we have in yellow, the sun, excellent color choice, with lots of great solar observing. And then this is the outer solar system out here. You can see Jupiter. Jupiter's going pretty well, right? We've got, there's a few missions there already. We've got Europa Clipper that's coming. And then there's Saturn is included. As you can see, this is very much not to scale. But Saturn is included with Dragonfly, which of course is a mission that's going to be going to its moon, Titan. And then we have New Horizons, which is somewhere out in the Kuiper Belt. But you'll see right off the bat, there are 2 big planets that are undeniably planets in our solar system that are not included. We're missing Uranus and Neptune. And of course, there is discussion about how and when we should be going back there. But they are missing from the current fleet. Okay, so I replotted this in a different way, just so the people at the back could see what I'm talking about. So just numerically, and then it's always fun to make things in a graph, because I think it really highlights what I'm talking about, right? Out to 50 AU, which is, Pluto somewhere sitting in here. This tail drops off. And it's not surprising, right? It is important that we look at the Earth. We're in a time of climate crisis, and there is a lot of good reasons to be studying that. But once you get out to 5 AU, 9 AU, we're talking Jupiter and Saturn, this tail is basically zero, right? The only thing that's keeping it a little bit alive is New Horizons, which is out of the Kuiper Belt. So, why bother? What are the big questions? Well, I phrased it in a way that I had to make everything a question. And the first one is really the unknown unknowns, right? What is it that we can find when we explore? And the quick answer is we don't know. That's the point of going back, right? We're human, we like exploration, we like going to new places. We go to the top of mountains, we go to the deepest parts of the ocean just to see what it's like. And this is equivalent to that too. But every time we explore, every time we go to a new place, we find something that is paradigm changing, right? And I think if you stay in science long enough and you're lucky enough, you get to have a moment that is truly, you witness that paradigm change. And I wanted to take a few seconds to just talk about my personal paradigm changing moment. And as it comes from New Horizons. So prior to New Horizons' encounter with Pluto, this is what Pluto looked like. This was this image, which is hard to see in these lights, but it was basically Pluto was black splodges and brown splodges, and this took a lot of work to make it. Pluto was a point of light, and we looked at Pluto, how it changed as Pluto rotated, and this map was made. Right? Pluto is okay, sure, that's Pluto. When I was on New Horizons, I was lucky enough to be one of the people that helped put the images together. I was on the imaging team, and we made Pluto, or the New Horizons data with people, made Pluto go from these brown splodges into this world, right? Pluto became a world at this point. You can argue whether it's a planet or not until the cows come in, but this is a world, right? There's stuff going on. And the paradigm-changing moment was almost the discovery of nothing, right? There's a region here on Pluto's left ventricle of its heart that has no craters. Right, this, I should say, this is shown in natural color. So if you're sitting on New Horizons, this is what Pluto would look like to your eye. But it's a lot more fun when you start stretching images and you really start to get, let me go forward one, there we go, an idea of just the color variation that we see across Pluto. And the region I'm talking about is this region here. And everything in the solar system is bombarded, right? We know that. So if you see a region that's not showing evidence of cratering, that's telling you that something's eroding those craters, right? The moment we saw this image, this one image alone, in my opinion, was worth the entire cost of New Horizons because it told us that Pluto is geologically active. Right? Now, that doesn't sound like a big deal, but stop and think about that. Pluto's at 40 AU from the sun. That's 40 times the distance from the Earth. If you were standing on Pluto and looking in the sky, the sun would look like another star. It would be a brighter star, sure, but it's not like the ball of orange light that we occasionally get to see from the UK. And yet, there's enough heat that this ice is overturning. So the heat must be coming from the core. Right? So the heat is permeating up, and it's kind of lava lamping the ice in this region that's overturning and eradicating those craters. And so some of the scientists looking at this, I'm not an interiors person, we're looking at this and going, well, maybe there's enough heat. If there's enough heat to do this, maybe there's enough for a subsurface ocean on Pluto. And if there's enough, if there's water, as Chris and other people talked about yesterday, if there's water and there's chemicals and there's heat, maybe there's life. And that's just an incredible thought, right? Pluto has no business having life. It's a long way from the sun. It doesn't have a nice gas giant to give it tidal energy. Like, if Pluto can have life, then what does it mean when we start understanding other systems? And we see these other worlds in other systems. All of a sudden, the chances of life increase a lot. And we only learned this by going there. We would never know anything about Pluto to this detail without going there. No, I've lost the, is it going? Oh, there we go. So, big questions. So what can we figure out, other than the unknown unknowns? Well, the first one, and when we go to the outer solar system, is lots of things are bombarded. And we can't see that on Earth. There's too much wind, rain. You see that in the UK quite a lot. But there's lots of erosional processes. But if we go to the outer solar system, then those things are preserved on some worlds. Okay, so when we start doing that, we can get an idea of what our own history was. What was the history of the Earth over the last 4 billion years? And this is one take on it that I wanted to show you. So this is a NICE model run for those people that know about this. If you don't, then these are the orbits of the giant planets, and they're shown here. So Jupiter, Saturn, Uranus, and Neptune. I didn't make a mistake. Those are the ordering at the beginning. And then the green bits are the Kuiper Belt objects. And I'm going to play this video, I hope, yay. And you'll see that the orbits of the giant planets are doing their thing, and then all of a sudden, there's a gravitational instability, and everything goes haywire, right? These green things get flung everywhere. Uranus and Neptune switch places, and we can't look at this, right? There's no time capsule yet, but we can see remnants of this if we go and look in the outer solar system. If we look at the cratering history of the solar system, and we look at different targets as a distance from the sun, and we look at worlds that are unchanged, we can start seeing whether these type of models are right. If we go to the outer solar system, we can tell what, history of our own world. All right, where are the requirements of life met? We heard yesterday a little bit, quite a lot about what are the requirements for life. And we covered a lot of this yesterday, so I'm not going to dwell on it today. But I think not everyone was here all the time, so I just wanted to mention a few of them. And my favorite's Enceladus. I was on the Cassini team. I got to be involved in helping plan observations for the thermal instrument for Cassini. I love Enceladus, right? This is my favorite world. It's about the same size as the UK, so I've got a bit of British pride going on. And we talked a lot about these plumes, right? And that's a place where life really could exist, right? We know there's heat, we know there's energy, we know there's chemicals. We talked a little bit about Europa as well. So this is Jupiter's large moon. Europa Clipper is going to go there and tell us a lot more about the surface. We think it may have plumes. There's been some discoveries that imply it has. There have been some that haven't been able to recreate those discoveries. But it's a really interesting world. It's got more water than the Earth. Right? So it has water, it has chemical energy, it has heat from that tidal interaction with Jupiter. It's a great place to look. But one thing that we haven't really talked about is similar worlds in the more distant outer solar system. And I wanted to introduce you to one of my favorites. This is, if it shows up, this is Triton. So Triton is a Kuiper belt object, we think, that got captured by Neptune. So it began life in the same part of the solar system as Pluto. Something happened, we don't know what. It got kicked into the inner solar system and captured by Neptune. The only time we saw it was when Voyager 2 flew past it in 1989. And so this is one of the best images we have of this really interesting world, and I'm standing right in front of it. One of the things that jumps out is what's going on at the southern hemisphere, right? What is all that black stuff that's all over the surface? This is an icy world. It has no business having black stuff all over the surface. If we look at a different picture of Triton, that's this one. The orientation's slightly different now. But you can kind of you can start seeing what looks like plume deposits, and that's what we think it is. Voyager 2 showed that Triton had plumes. These plumes, we'd never seen cryovolcanism before, like ice volcanoes, right? This was the first time that we got to see these things. And at the time, it was considered that probably they came from greenhouse heating. So you had thin ice layers that were transparent underneath. You had pockets of air. The air heated up when the sunlight hit it, and that caused an explosion, which brought up with it material from below. There aren't many ground winds on Triton. The winds are high up, so this material went straight up, but unlike Enceladus, where it escapes, Triton's bigger. It doesn't escape. Instead, it gets caught in the high winds, pulled across, streaked across the surface, and eventually lands on the surface, forming these fans. Now, since then, we went back and we saw Enceladus, right? So now we have a completely different mechanism of how cryovolcanism can work. And these plumes dump out about twice as much material as Enceladus does per second. So it is feasible that these are more Enceladus-like than greenhouse-like, like the idea that it's coming from a subsurface ocean and spitting straight out. And just to kind of highlight how cool these plumes are. This is an artist's impression, if I can get it there we go. So of course, take some things with a pinch of salt, but this idea that the plumes go straight up and get whisked a lot must be an incredible sight to see. Triton is a really, really interesting place, but we don't know much about it, right? We had one encounter, it was a flyby, and we saw the illuminated side, which is the good side to look at. But if you plot it onto a map, if it was complete, this would fill the screen, right? So you can see this black bit up here. We have no idea what lurks in that bit at all. But we know, so this bit, no idea. Oops, a daisy, come on. But we know as scientists that if there's a region of the world, or that there is either going to be aliens or dragons. Those are the two options, right? It's clearly one of those two. Okay, it's probably not. It's probably more ice. But if we understand what's going on in either, in this northern hemisphere, then we can start testing this plume theory. Do we see more plumes in the northern hemisphere? What does that look like? This region is vast. It's about the same size. It's about 9 million kilometers squared, so it's about the same, just a bit bigger than the continental United States. And this is a region of our solar system on a world that we think is inhabitable that we've never even seen. Right? That's just something rife to be explored in my mind. And when we went back and we made these discoveries, we used 70s tech. Right? So this was an encounter in 1989, but Voyager 2 was launched in 1977. And the idea was conceived in 1972. Right, this is 70s tech that we took these images with. Now, I don't know if you remember the 70s. I do. I'm not going to admit to whether I know them or not. But it was an era. And the tech that went with it was special, right? If we wanted to listen to media, if we wanted to record media, the most common way was on some form of Walkman. There were mobile phones, cell phones. They were invented in the 70s. They really came into their own in the 80s, but they were around. The Apple computer should show up. I don't know where to point this. There we go, the Apple computer. You got kilobits of RAM. Very different, I know, right? Don't all write home at once. And then finally, there was the first sort of handheld digital recorder that had 32 by 32 pixels. Right? So you have more in your cell phone in your pocket, in your mobile phone, than most people did. And of course, space flight's been on the cutting edge of technology. Better technology is available to Voyager than it was to most people. But just think of the technology that we have right now and the technology we hear about today. If we go back with that sort of technology, what will we find? Right? We'll be able to see things at a higher resolution. We'll be able to see things at different wavelengths, at different wavelength resolutions. There is so much to be discovered. So, next big question. This is the big one, really. Does extraterrestrial life exist in our solar system? So Chris showed a little bit of this yesterday. There are these vents on Earth. This one was taken 3 kilometers below sea level. It is dark, right? If anyone that does scuba diving knows that the light goes away fast. 3 kilometers down, it's dark. There's no light energy, but there's heat that's coming from the Earth. There's minerals that are coming from the Earth. And that's enough for life to exist, right? You don't have to be an astrobiologist and understand DNA in order to know that them be wiggly things that are alive, right? And so where might this exist? And I think that's a really key part of what we're talking about. And of course, Europa and Enceladus, maybe Triton, maybe Pluto offer those things. And they're all in the outer solar system. Right? And I think it's going to be great to fly through the plumes. I'm all a big fan of Star Trek's first directive, do no harm. Flying through plumes is nice because you never damage that ecosystem. But I think as people, we're never going to be satisfied until we know what wiggly things are underneath Enceladus or what underneath Europa. And I think there are some projects like this is IceFin, which is being developed at the University of Cornell, that are trying to do that, to come up with the technology to get through kilometers of ice, to not damage the ecosystem, and to see it. Absolutely phenomenal. Okay. And in my last minute, the final big question must be, how does that life extend elsewhere? Right? If we're just going to look at statistics, we've all heard about exoplanets. We heard a lot about them yesterday. But we need to understand our own solar system to apply that logic to other worlds. Right? We've got this backyard, relatively speaking, of these different experimentals, these labs. And yet, if we don't understand those, we can never apply them very well to other worlds. This is an artist together, lots of the Kepler discoveries, and they're shown in brightness temperature. And this is only a handful, obviously, of the ones that have been discovered, but a really beautiful illustration of the diversity of exoplanets. And in order to understand those, we need to understand our own solar system so we can apply that logic elsewhere. So my takeaways, I guess, is the unknowns, how to understand ourselves and how to understand where life is outside. We have to go to the outer solar system. And I want to see it, right? I want us to go now, so I get to see it in my lifetime and in your lifetime. Because there's worlds out there to be discovered, and we can explore them together, and it's going to be great. Thank you. Should I leave that somewhere?